nicotinic adenine dinucleotides, is that right? That's NAD. Fulving adenine dinucleotides, that is FAD. Okay. Monoadenine dinucleotides, that is FAD. Iron sulfide, FES. Coenzyme Q is a ubiquinol, it's a quinol. Cytochrome C, AA3, and oxygen. And we mentioned about here, some bacteria need an enzyme called oxidase. That's why we have an oxidase test, and we call it a cytochrome C oxidase test. There are several things we want to mention, okay? I'm going to draw right here. First of all, you need to know where is the location of electron transport chain. That will be the first question you usually ask you. What is the location? Bacterial cell, as a prokaryotes, where it is? Cell membrane system. It's very simple. Okay, how about fungi? Yeast and molds, where are they? Can you tell me in 5 seconds, where are they? Matt, where are they?
The mitochondria?
Yes. Because eukaryotes, is that right? Mitochondria. Okay. Now, we don't talk about this. You already read it. Okay, so we're going to focus on right here is bacteria. Now, here is the question. This is the first question, the location. Second question is the order. Why the order is like this? Why NAD, FAD is always at the top and oxygen is always at the bottom? I want to mention this because there's a concept we will mention regarding fermentation, respiration. Otherwise, you won't understand. Why is it like that? So this is something we want to talk about. The electron is always transferred from a donor to an electron acceptor. Now then the question will be, how do you know it is a good electron donor? How do you know it is a good electron acceptor? This based on so-called two-half reaction. So what is two-half reaction? Two-half reaction said very simple. Oxidase reduction half reaction. It is test the value, the capability of the bacteria to transfer or accept electron. And they use a volts value to as a measurement. So I give you a very simple example. If NAD with proton, with electron, then they become NADH2. What is the voltage value? The delta E. Minus 0.32. This is a guy like here. But how about oxygen? If I have a reaction right here, what is that? Positive 0.82. This is a negative value, this is a positive value. Once you see it's a negative value, the more negative, the better electron donor. Or we say transfer, but we just say donor. This is very positive. The more positive, a more better electron acceptor. Then Y, same thing as delta G. Once it's negative, there is a spontaneous reaction will happen during the electron transfer. Once it's positive, unless you have other thing to do, it will not break. Water is very stable, is that right? What's the only way to let the water come out? What's the way to let the water come out? Middle school chemistry. Electron, is that right? So that's why for the industry, they will work with salt. Break down. Become this guy. Hypochlororic acids. It's a free chlorine. That's why it comes out with this. Because water is very stable. Because delta G is very positive. Okay? And based on this two-half reaction, we already measured. You can see from the top to the bottom, the value is become more and more positive. So, this is minus 0.82. I believe FAD is minus 0.18. You can see cytochrome C. Cytochrome C is starting to become positive, 0.25. Cytochrome A, A3, you can go ahead to see, is about 0.35. And the last one is 0.82. At the beginning, it's all negative value. And later, it's a positive value. These are good electron donor, and later on will be a good electron acceptor. Another thing I also want to mention, you already know, NAD, if they reduce to NADH2, how many ATP generate? All the time we talk about 3 ATPs. Right now we talk about 2.5 ATPs. Is that right? Because we talk about the oxygen phosphate ratio. How many ATP generate during the FAD become FADH2? This will be minus 0.18. It is 2 ATPs in the older calculation. Right now is 1.5 ATPs. Why? Why the electron transfer from NAD go oxygen is generate more energy compared to FAD to oxygen? This is because of distance. And have another color. So what's the distance here? 0.82 minus 0.32. That equals 1.14. How about right here? 0.82 minus 0.18. That equals 1.00. This voltage value is the distance from NAD transferred to oxygen is larger or greater than from FAD to oxygen. So this process generates more energy. So here comes another thing. Is more distance values of electron donor to acceptor, the more energy ATPs generate. Okay, this is something I also want to mention. Then I also want to mention last year, you always remember electron carrier. Regardless of NAD, FAD, all these things, they must be recycled in their lifetime. Which means, no matter how complicated it is, NAD reduced to NADH2, they either do itself back to NAD plus, or there is other chemical can couple it. Otherwise, the bacterial cell will be died. This is very simple, because you don't have anything to carry on the money. You can buy food. You don't have wallet. It's very simple. You don't have anything to carry on the money. You don't have hands, you don't have wallet to carry on the dollars. How are you going to buy the food? You say you use credit card, but that's still a carrier. Is that right? So that's something always remember. The electron carrier must be recycled. In the bacteria, microorganism life cycle, if they cannot be recycled, bacteria will not be survived. Okay, so this is something I want to mention. Last one. Before end, we also want to mention. There is one theory which is we call it oxidative phosphorylation. What is oxidative phosphorylation? Which is related to electron transport chain. So what is that? This is the one we have to draw right here. We take this out. And I use this electron to give an example. Okay. Inside we mentioned about. This is the cell membrane system. So we assuming this is the inside. And this is the outside. So the electron is transferred from NAD, FAD, FES, cytochrome C, coenzyme Q, go to oxygen. Once the electron is transferred, something will come out. What is that? That's H plus hydrogen ions, or we have another name called the proton. They will be accumulated outside of the cell membrane system. This is proton that accumulated. Now, why they can do that? Because there is a NAD dehydrogenase is there. What means dehydrogenase? Which means they let NADH2 back become NAD and release H proton. And these protons accumulate too much inside of the cell, they will be repelled out and they accumulate outside of the cell membrane. The more and more they accumulated, they will generate a potential energy. And this potential energy, we call it proton motive force. PMF. So they accumulate. Once they accumulate two more, what are they going to do? You always remember, there's a feedback. You treat people nice, people will treat nice to you. If you treat people too much, they're going to come back. Okay, just give an example. So what they do? This is going to go back someday because it's too much. This is to give you a very simple example. You repel all the people out of the United States, so one day they're going to go back. That's a very simple example. You understand? The same thing for bacteria. Let's say this is a wall. It's a border wall for the bacterial cell. Okay, you repel too much, they're going to go back. Once they go back, what do they do? There is an enzyme, it's ATP synthase. This will be activated. What's the function of this one? Is ADP with phosphates becomes ATP. This guy is activated by proton motive force. Once this guy happens, what happened? Bacteria started to do rotation. This is rotation related to an important structure of a bacterial cell, is flagella. This whole theory called chemosmosis. It is a British scientist, Peter Mitchell, in 1932 published a paper describing that. And later on, people recognize it's a big contribution for the scientific area. This is 1959 or 1962 Nobel Prize for that. This is well explained as the electron transport chain related to the energy generator. That is we call oxidative phosphorylation. That is where comes the oxidative phosphorylation is related to the electron transport chain. So based on this, you will see substrate level phosphorylation, because really we look at the chemical itself, the energy transfer potential. And this is we talk about the electron transport chain. So if I'm asking you, what's the difference between substrate level phosphorylation? If you simply tell me because they are not related to electron transport chain, that's a very vague answer, to be honest. You see the principle behind it is completely different. Is that correct? So that's what's the two principle right here is we talk about is substrate level phosphorylation and the oxidative phosphorylation. So what's the key here? What is ATP? Why the ATP is a currency? What is substrate level phosphorylation? What is oxidative phosphorylation? That will be the key for these slides. Okay, so I think we're going to end off here. Then we're going to go over these slides and talk about enzyme next Tuesday.